Welcome to ninth lecture of course on tribology. In last lecture, we have discussed wear mechanisms. We are continuing in this lecture similar kind of a wear mechanisms. We have covered abrasion, adhesion, corrosion, and the last one slide we started with erosive wear. We are going to continue with erosive wear. In addition to that, we will be treating or we will be learning additional two mechanisms. One is a fatigue and other one is a fatigue. They have a lot of similarity. We will be discussing those. This is the last lecture slide, erosive wear. We said that impact energy is required or kinetic energy is required to initiate erosive wear. Particles either solid or liquid, they should come with some velocity, impinge on solid surface and impart some kinetic energy to the other surface. As this is a moment transfer, so angle of impact will be an important parameter. Similarly, is related to kinetic energy, it will be the mass of particles as well as velocity of particles will be related. That is why we gave this equation. We say the V E is a wear by erosion, wear volume by erosion, that is a empirical constant. A as a function of alpha, alpha is the impingement angle, impact angle, I as a function of V is a velocity function and m as a function of particle size. Increasing the particle size will increase the wear rate. Increasing the velocity will increase the wear rate, and impact angle will affect one way or another way, depending on what kind of material we are using. Whether the material has tendency to absorb the energy or it has a hardness to resist the wear. So, depends on these two properties, wear rate will be decided. Now, first let us define impact angle in absolute manner. So, the impact angle not necessary particle coming from 10 meter away, and we need to think about what is the angle of inclination, but just before impacting what is the velocity what is the angle of impingement just before the impacting the solid surface, that will affect the result. So, we say that impact angle is angle between eroded surface which is going to be rotated and trajectory of the particle immediately before the impact. If impact angle alpha is initially very high or very low, but is changing at the last moment, then we will be counting only last moment angle, that will be alpha, that is impingement angle, that is impact angle. Both the things either is a low angle or medium or large angle, characteristics will be different. If particle is coming at the low angle, angle of inclination is lower, value of alpha is lower, like either 5 degree, 10 degree, 15 degree, then particle shape will also matter. How it is going and colliding with the surface, we know very well the kinetic energy will not be transmitted that much as kinetic energy can be transmitted by 90 degree alpha or alpha equal to 90 degree. But in this case, the shape of particle will affect the wear rate. It will try to abrupt the surface, it will try to cut the surface, it will work as a cutting tool. So, particle shape will matter in that case, and to resist the wear, to reduce the wear rate, hardness of the substance need to be higher, hardness of this component need to be higher. Coming to other side, if the angle of impingement, if angle of impact is higher side, 75 degree, 85 degree or 90 degree even, then we require softer material, because most of the energy is getting transmitted to the substance or component. So, softness is required or which has a more toughness, material having a more toughness will be important, which can absorb the energy. And most of the time the softer material have more toughness, have the energy absorption capabilities. They can deform by absorbing the energy, wear rate will be reduced in that case compared to harder material, which will fracture the surface itself. So, we have different treatment for low impact angle, we have different treatment for large impact angle. And this diagram shows identifies clearly what is the role of impact angle. You can see the impact angle is on x axis, wear rate is on y axis, and 0, 30, 60, 90 degree has been quoted. For cast iron, which is a harder material, as impact angle increasing, the wear rate is also increasing, because the cutting action it can resist, but energy absorption it cannot be done. So, that is why the cast iron at high impact angle should not be used. Taking an example of softer material, that is a rubber, elastomer, which can absorb the energy. Initially, the wear is very high, because they cannot be cut, they have a very low resistance towards a cutting, it can be simply chipped away, a layer can be simply separated, but under compression they can resist much more force compared to the shear force. That is why the low impact angle, which imparts more shearing or cuts away the surface, is not required, or we say that we should be avoided. Wherever there is a high impact angle, more energy is getting transmitted and particle is subject to more compressive load, rubber material can be used. So, these are two examples show that what is the importance of impact angle, and if we know characteristics of the particle, what is the impact angle, we can choose proper material for that situation. And this is what it shows that if impact angle is 0, impact angle is 0, I am talking about absolute sense 0, then there will not be any wear rate. That is why this initial curve does not show anything, it is not touching the surface, impacting it is not coming in a contact at all, right. So, wear rate will be 0, it does not matter to us that we choose any material, does not matter. Now, there is another constant of this, say the k is empirical constant in this equation. If I go ahead with similar equation what was given by Archer, I can assume that k is a probability of wear particle formation. Wear particle formation means the particle is getting dislodged, is getting removed from the surface. What is the probability? The k, we can say in general term, the k is the probability of that particle formation. So, lesser the k, better the results. If you can reduce this k, it will provide very good results to us. As we are dealing with the wear, and where we know that is a system property, it is not a material property. Whenever we talk a system property, the number of parameters will affect the results. I can change the design, I can change the parameters, or I can change the material properties for getting good results. To illustrate that, let us take one example, is related to the pneumatic transportation. The pneumatic transportation means air or gas is being used as a carrier fluid to carry these pallets. The green colors, these are the pallets, maybe spherical in shape. The pneumatic, or we say that gases carry this from one end to other end, and the major problem comes wherever there is a change in angle. If these particles are moving in a parallel pipe, straight pipe, they will follow straight path, not much impact angle, no impingement, there will not be much wear rate of the surface. But wherever there is a elbow or the band comes, then there is a 90 degree change, particle material need to be changed accordingly. We have heard in previous lecture or previous slide, we have discussed that if impact angle is high, we should use a softer material. So, this is related to same thing. So, that initially maybe some other material was used, now we are trying to use steel pallets, I mean the same system is used for steel pallets. Steel pallets having a relatively more mass. So, if you push it, will cannot get more kinetic energy and will cause more wear rate of the pipe. In addition to that, we want to increase the speed of transportation. It is not only we are changing the mass, we are changing the density, but we are changing the velocity also. We want to go ahead with the higher velocity, and we know that kinetic energy is proportional to v square. Sensitivity is increasing. If we increase the velocity, that square effect is coming into picture. So, we need to think about which material will give the good result. As I think from a conventional point of view or a simple without much knowledge, you can say we can reinforce the elbow. Reinforce means that we can provide some sort of rubber padding inside the pipe, inside the elbow, that will sustain impact or that can absorb the impact. However, the question comes, will that be find a good solution to us? First thing is that we need to change the elbow, we need to coat it. Is it simple or is it easier? If it is easier without much cost, then we should go ahead with that. However, we find that is slightly difficult. In addition to that, not necessarily all the particles are impinging at the 90 degree. There is a possibility the few particles are impinging on the 5 degree, few particles are impacting at the 15 degree, few particles are impacting at the 25 degree, depends, because there are number of particles and probability may vary from 0 to 90 degree. One thing is that of course, the mean value will be on the higher side, will be maybe 70 degree, 75 degree, but still there are particles which are getting are impacting the rubber material at the lower angle. So, rubber will be weaker, and once it starts shearing, once it start developing crack, then it will cause failure. So, again we need to replace that kind of elbow very frequently. That is why we are saying that reinforcement and the quick change in elbow. Maybe initially we were changing this elbow after 1000 hours operation, or maybe we can think about changing this elbow after 100 hours. Assembly, disassembly will be a problem in that case. It will take more time, more material cost, more labor cost, and shutdown of the system for some time. Another option we can think about the redesigning the shape of elbow. Instead of sharp 90 degree bend, we can think about changing the length on the longer side, and very gradual curvature shape we can give with instead of 90 degree bend, we have a bend of maybe say 10 degree, 12 degree, 15 degree, and then the similar kind of raw material can be used. But we need to redesign the system, we need to have different kind of assembly, because we are going to increase the length of the pipe. 90 degree sharp bend, pipe length may not be that high, but when you go for the gradual change, the length of the pipe is going to be increased. We say that another one is that you choose totally new elbow, do not reinforce, you change complete elbow material, go over the multi-grade materials, or maybe use a rubber material with some sort of hardening effect, so that it can do a number of experiments on that and choose a best material, or after doing a number of experiments which will suit completely for this kind of problem. I am using the word, this all solutions are conventional, it can be thought over easily, but if we are understanding the wear mechanism properly, we know very well wear will take place after some time. It is not a spontaneous process, it is going to take few cycles, a few cycles maybe 10^3 cycle, 10^4 cycle, 10^5 cycle, 10^6 cycles. Can we utilize that as an advantages too, or can we think from that angle and guess, okay, if this is the situation, can I think about the temporary layer which gets formed and deformed and removed without causing any failure? Can I think about some layer? Self-made system itself has a capabilities to make layer, remove layer, and then form a new layer. So, without much damage, maybe some damage, maybe say 0.01% damage is fine. If that is when we can think about some layer, and this is the equation is given, I can reduce a k because IV is going to increase, M is going to increase. Angle of impingement, initially we showed that the redesigning the shape of the elbow can be adjusted, but if I do not want to do change in that, the A alpha will remain same, I will is changing because of the input velocity is increasing, M is increasing. So, both these increasing, the wear rate is going to increase. If I want to reduce the wear rate, I have to play with the k. That means, I have to reduce the value of k. That value can be reduced by reducing the number of particles which are impacting number of particles which are impacting the pipe. If I can reduce this probability from 1 to say 0.01, I may get the same result. I can get same life of the components. So, in that case we can think from innovation point of view. We can say that these are the steel balls and will get attracted to other magnet. Can I think about the electromagnet? Attaching electromagnet on the pipe is something like this. There is an electromagnet very near to pipe. Whether this pipe is magnetic or non-magnetic, that does not much affect the result, because the magnetic field will vary. If this is a non-magnetic, still electromagnet can be used, because we are thinking of the steel balls. Interesting thing is that whenever we are using this kind of electromagnet, all steel particles will be coming near to the surface. So, if I can control electromagnetic field, provided just sufficient field so that one layer is formed, not any other layer on that, then what will happen? There is a possibility particle comes, impact one of the ball, remove this ball because of the moment transfer and get attached to the surface. So, this will be a continuous dynamic process. One layer will be there always. Few particles will be removed, few pellets will be removed in every cycle, and new particles will come and replace it. So, we are bringing almost to negligible probability of impacting on the surface. Whatever the particle comes initially, they will be remaining, and maybe say out of 1000 particle or 1000 pellet, few maybe say 4, 5 or 10 will be removed. So, we are coming down to very low probability. This will be effective method to reduce the wear rate. We are not changed material, we have just changed the system design. We added few more fields. Instead of just mechanical field, we have added a magnetic field to reduce the mechanical effect of the particles. So, this is the one way to deal with the problem. When we talk about the wear, so if we understood the wear, we can think of in broad sense, we can come out of the box, or we can think out of the box and get a good solution. Much mature solution, much more reliable solution, much quicker solution. Let us take another problem. This is design of filter design, maybe say of aircraft engine, or maybe say the helicopter engine, which remain at the some height where the generally sand concentration is very high in the air. And what is the purpose of this design is that we want to suck the air, so that combustion can take place in engine. That means, air is sucked and supplied to the engine, but we know very well whenever the air is sucked, sand particles also will come along with that. So, we require one effective filter, but we know very well if you use a filter over here, then it will reduce the pressure. That means, we have to boost the pressure, we have to compress the gas, and we need extra system for that purpose. To avoid that kind of pressure loss, generally they use this kind of design. They use a particle inertia. You say particles are coming with some velocity when it getting sucked, and they will move in simply in this zone. Air which can skip from that route, can change its route, because it has a very low inertia, can come this side. The problem is that to increase the volumetric efficiency, we require really very large volume, the volume of the air. In addition, this is not a foolproof method. Still, there is a possibility the few particles will come. If the particles are coming and hitting the engine cylinder or combustion chamber, naturally there will be a lot of problem in engine operation. It can fail anytime. However, there are system designs, we use redundant engines, so that even if there is a one engine is failed, other engine parts are working, or other cylinders are working properly. That redundant design is possible, but can we reduce this wear rate by changing the system design? There is a possibility. We can think about it changing in filter. This is a factory of one filter design. We are trying to scavenge the sand particles from this route and air through this route. We can change the route. There is another possibility, we can increase the volume of this duct, so that more air can be sucked. But problem is that for any flying object, a lesser weight will be preferable. We require lesser driving force in that case. So, minimization of weight will be one of the major constraint, minimization of the volume will be a major consideration. So, if I want to increase the volume of this, that will not be acceptable, because that is going to increase the volume, increase the weight, and we require more driving power, which is not very sound design. So, there is a one patent in which was done in USA in 1995. You can see there is an inlet change in design, there is an inlet suck, and we know the particle we were trying to we are generating a hindrance. So, the particle can come and impinge on this, an angle is almost 90 degree. After that there is a parallel particle change and direction is parallel to this. So, I can use this as the proper design of material. Of course, design is already there, we can choose proper material which has a high impact angle, and air has a skew root also. As there is a change in curvature, particle will not be able to climb that much. Few particles which are climb and again come back, it will not be having that much energy, or we say maybe having energy, will be a number of particles will reduce effectively, and we will be getting sound design. It has been proved that performance of this kind of design has improved engine life by 40% or reduce the wear rate by 40%, which is substantial high. You change design and then get a good result, that is really very good. You say that we can think about this one material of lightweight material. If the not rubber material is suitable, then we can think about some alternative material which can absorb the energy, doesn't resist too much, and you can see the kind of the shape is more like a finger shape which has a lot of flexibility. This particle comes and impact it, this will be slightly flexible. If anything system is flexible, it will not wear out very fast, unless the fracture occurs over here, this cross section itself. If the fracture occurs at this cross section, that is fine, but this can we say that will be a fatigue problem, and we can design from fatigue point of view. Maybe we can design this system which has a more than 10⁻⁶ cycles, 10⁻⁷ cycles, or 10⁻⁹ cycles. That depends on what kind of design we require and what is the life of the system. Many times when it comes back, we can replace this material also. Now, we are coming to the new mechanism, what we call the fatigue wear mechanism. Even though I am using the word a new mechanism, but I should say that almost all wear mechanism are one way or another way related to fatigue wear. We started with abrasion, then we brought the probability into picture. Probability says that particles are not going to immediately dislodge from the surface. They will go under plastic and elastic deformation, and after certain duration only they will come to the 0. That will come it will be dislodged, it will be removed from the surface. So, fatigue one way or another way is related to all mechanism, it is related to adhesion also. We can give a formal definition. We say that fatigue is attributed to multiple reversal of the contact stress. That means, particles are coming into contact, solid surface are coming into contact, and this stress is induced and relieved also. That is a call we are using word multiple reversals, that is the load is applied and removed. It is not a constant load. We can think about the asperities continuously, the particle when the surface is sliding, asperity comes under load, bends and regains its shape. So, load it and unload it, that is a continuous process. We have number of examples related to the fatigue wear. We say that it is a common process, it is a common phenomena in rolling bearings. That is why the rolling bearing have a definite life, that is generally calculated based on the fatigue theory. Similarly, gears, contact wear really governs gear failure. We know very well that gear failure can be predicted, can be estimated by using two theories. One is a bending theory, other is a contact stress theory or hydrogen theory. And 99.9% the failure occurs because of the contact stress. Fatigue bending does not cause much failure. Factor of safety by and large is almost 3 to 4 in bending, while contact stress factor of safety it turned out to be 1.4, 1.5. All friction joys unkempt follower mechanism. Rolling action is rolling fatigue is governs overall wear mechanism. But there is another possibility, that fatigue by sliding contact, and that is more common at the localized one when we are talking about asperity level on a micro or atomic micron level or nano level or atomic level. Just to illustrate what I am trying to convey, let us take this is one line is shown, that is a surface layer. I am talking about the front view of the surface, and surface is visible as a line, and one asperity is there, that shows the irregular surface. Now, if I apply a load on this asperity, either it has to fracture immediately, which 99.9% will not happen. It will change the shape if the load is applied. So, other substance, other material or other component comes, passes this surface. When this passes this surface, it regains its position. But what is there? When it is changing the position from straight to the band position, it is subject to the stresses, the tensile stress and compressive stress, and it is happening a number of times during sliding motion, number of times. So, truly this is a bending problem. Now, I can deal as this as aberration, or I can deal this as a adhesion, does not matter. Basic micro level phenomena is fatigue failure, and this is one typical example which was also shown in the first lecture. You can see the pits generated on inner surface of outer ring. This is the pits generated, and this is a fatigue failure. We know if we use this kind of ring again, bring in operation, there will be high irregular performance, lot of noise will be generated, and this will at the end of the slide say that abrasive and adhesive wear involve a large contribution from the fatigue, even though we are using word abrasion or adhesion, but they are basically governed with the fatigue. Just to illustrate slightly in a detail, let us look at this slide. There is one figure which says that top layer is a different color, second layer slightly different color, and then parent material, and we are showing some sort of a deformation lines, that this line is representing what is a what kind of strain is developed in a surface. We know if we try to move surface in so we try to supply some sort of sliding force in this direction, top wear will be sustaining maximum strain, then intermediate layer, and then final layer. Final layer does not have anything to sustain, it is a superficial phenomena. So, it will happen on the top surface and to some extent below that surface, which that is why we say that this top surface is a very highly deformed material, the shear deformation of the material, then moderately deformed, and this is almost undeformed surface. Now, overall fatigue behavior will depend on the T. What is the thickness of T? We are thinking many times this T is a outer layer. When we talk about the bimetallic layer, we talk about the trimetallic material, where the 3 layers are there, or we talk about the multi-grid material, when the number of layers are there, number of materials are bonded together to give the suitable performance, then this T really affect the results. And we say that T majorly depends on the coefficient of friction. If the coefficient of friction is very high, actually we have to apply more and more sliding force, and more and more sliding force, then more and more grains will be deformed in this direction, they will reorient to a certain limit. And in every case, whether the load is low or high, maximum compared to, when you talk about the comparison between 3 layers, maximum strain will be on the top surface. If you increase the load, then what will happen? At the interface, there will be some sort of void formation, which we have seen number of times. When you talk about the rubber material, you bend it, you are able to see some sort of pores in rubber material, that is a void formation. If there is a void formation, that means there is no material. stress area is almost or the area which can sustain stress is negligible, and that can be teared away easily, that layer can be chipped away easily. Wherever there are too many voids, fracture will occur easily, that will remove the complete surface. That is the reason when we say that T is smaller, when you are talking the bimetallic material and top layer has a very small thickness, more bond, then lesser number of voids will be generated because of the more bonding, but thickness is more on a higher side, then the bonding will be slightly lesser and more voids will be generated, and delamination of that layer will be much easier. That is why I say that we need to design thickness properly, or the surface which is undergoing very high shear rate need to be designed properly. Sometimes we find the surface crack itself. What we talk about the void generation, and that will be more like a subsurface, but there is a possibility of the surface cracks. Surface cracks we can think very simple manner, roughness. Surface roughness itself has some asperities that is going to create a problem, and that is why I shown over here. There is a asperity over here, and if it is a reciprocating motion keeps going on, this depth is going to be enlarged, will be getting extended. Something is clearly shown in the sketch. When we move this surface over this surface, and there is a possibility of piling of material. We know very well when we drive in a muddy road, mud will get piled up in front of the tire. Same thing is happening over here. Material is getting piled up, and this crack which will come directly in front of the load, then it will elongate it, something like this. When the elongation keeps going on, and again the material comes, or the force comes immediately on this surface, it will turn out to be a delamination, a removal of that particle from the surface. And this is one of the common phenomena happens in the gears. You can see gear pit over here. If this kind of wear particle comes out, maybe in the order of few microns only, we are able to see the pit on the gear. Whenever there is a pit on the gear, sliding will enhance, pure rolling will reduce. If there is a reduction in pure rolling, increase in the sliding, that is going to cause further more and more tangential load, or require more tangential load on the surface. More tangential load, more crack formations, more wear particle generations. So, we can say when we are understanding this kind of mechanism, now we can explain one slide which we have seen in a previous lecture or previous lecture, where the high mu, high coefficient of friction, but low wear volume was estimated for some materials. On other hand, low value of coefficient of friction, but high wear rate was estimated. Otherwise, as per the Roy condition, wear volume will be related to square root of 1 plus mu square. That means, it is directly related to the friction. Increase in the coefficient of friction means increase in wear rate. However, when we are talking about the fatigue, when we are talking about fatigue mechanism, we can explain these are not 100% related. For most of the material, yes, they are related, but not for every material. So, we will just come back to that slide which we showed in previous lecture. You say that in this case, as a coefficient of friction is decreasing, wear rate is decreasing, but here coefficient of friction is increasing again, but still the wear rate is decreasing, right. Now, what are the reasons? Quite possible material combination which we are using, they have some sort of inclusions, they have some sort of manufacturing defects. If they have manufacturing defect, if there are voids, cracks will form a fracture surface, or a surface which can be easily fractured or delaminated from the material, even though they can show low coefficient of friction. Talk of the carbide materials, when carbide is rubbed over the steel, coefficient of friction may be very low value, but they have cracks, they have voids. When they are getting combined, they make a surface which can be easily fractured. that is why the wear rate will be high, even though coefficient of friction is low, but wear rate is high. Take another example of copper. Talk about the 99.9% pure copper, no void, no inclusion, high coefficient of friction maybe 0.6 plus, but wear rate will be low, because fatigue will not be there, or fatigue there is no crack generation or a void. So, that material will not wear out very fast. So, that kind of mechanism allow us to understand what is the difference between coefficient of friction and wear rate. They are not always related, they are not always in harmony with each other. Quite possible high coefficient of friction, but low wear rate. On the other hand, low wear rate, but high coefficient of friction. And understanding this kind of mechanism help us to design better and better systems. And what we are adding in this slide is a plane of weakness. If the material has a planes which are weaker, that means they are weaker than surfaces, then wear rate will be high, or if there is inclusions in the material, wear rate will be very high. We will discuss later about this when we cover one case study in next lecture, how inclusions can create a more problem. We discussed fatigue due to sliding or during sliding motion, but there is another fatigue which is more common, that is what we call as the fatigue wear during the rolling. We know very well rolling induces very high concentrated stresses, or we say that contact stresses are generally very high in rolling motion, because area of contact is very low. So, what are the possibilities? You say that the steps which are leading to the fatigue wear, first that we are applying a normal load that induce very high stress at the contact points. Believe me, contact stresses in bearings are almost 2 to 3 gigapascal, which is very difficult to imagine. We say steel has only 560 megapascal as a strain, how can it sustain a 2 gigapascal? That is a 3 times. Factor of that is just 0.3, and still the bearing can show number of cycles. So, that is very contact stresses are very different than the tensile stresses, and they need to be have a different kind of equation, different kind of behavior, or different kind of treatment when we try to solve the problems. They are more or less compressive in nature. That is why we use a material which are stronger in a compression compared to tension. By and large, we have a common thinking of steel or iron and all ductile material, they are similar, they have similar behavior in compression and tension, but it does not happen with all the materials. When we work hard in the surface, it will have a more compressive strength than the tensile strength, and we want to bring the compression strength to even a 3 gigapascal plus. So, that results are favorable to us. Now, when we apply a very high, not very high normal load, but we apply a normal load which induce high contact stresses, there is a possibility of elastic and plastic deformation. Elastic deformation is not a problem for us, it will regain the shape, but there is a possibility of the plastic deformation, some sort of depth in that. And once there is a D shape comes on the surface, then problems will start. We say that after D shape or plastic deformation, there will be a subsurface crack nucleations, possibility that the D shape itself is generating a nucleus or providing a nucleus for the crack. And on reversible loading, continuous loading and unloading, there is a possibility of expansion of the crack, subsequent to that extension, and finally generation of the wear particle. I can show you all this image whatever we discussed on this slide using some pictures. You say this, let us check this in A, surface is slightly irregular, we are talking about the loading and unloading, reverse of the loading. So, loading is a compression, when the load is reversed it should come to 0, but there is a possibility of residual stress. We are loading something in compression and relieving it, quite possible in lateral direction. We know that the new factor, lateral direction there will be tensile stresses, and that tensile stress can generate some sort of a nucleus or some sort of voids in a material. If number of voids they come closer to each other, they will make a bigger void. a larger side void, and if it is loaded and unloaded continuously, this void will extend up to the surface and a whole chunk will come out that will generate a pit on the surface. So rolling as well as sliding are generating the pits, but with a different kind of mechanisms. Here the lateral direction force matters a lot. It deforms the surface in compression, but when the compression load is removed, then it gets expanded. When there is extension on that, then we are getting tensile stresses on the perpendicular direction. What I am trying to say, that if I am loading this surface, compression is increasing, but when we are relieving it, material has to relax it. So, that is why the stresses will be generated in a perpendicular direction, this direction and this direction. That is why the crack is nucleated and expanding towards this direction. It does not come directly under the load, it is going beyond this side and this side. That is happening because of the lateral crack or force or tensile stresses which are in lateral direction. So, the end of the fatigue comes with the cracking. Many times we have we apply a very high load on the surface, not intentionally, but because of the some malfunction, some sort of overload or some sort of misalignment or some problem in assembling the components. Then what in that case happens, very high load will generate a crack through and through from top to the bottom surface, and that is known as extreme case of the failure. That may happen as spontaneous also within few hundred cycles. We talk whenever we talk with the fatigue, we talk about large number of cycles, but this may happen even 100 hours or not 100 hours, we say even 100 cycles. So, what we say, the cracking is ultimate failure, it may be instantaneous also. It is going to split the component. When the component is split, naturally it will not have any function or functionality will be 0. It is a complete failure, it cannot sustain, it will not, we do not have any time left for its operation. Majorly happen with excessive load, but here in addition to excessive load, the vibration is also there. The vibration of the reversal load is there or some sort of impacting is there, then this kind of failure will occur. When we are talking of the vibration, we are talking along with the loose fit. If there is a firm fit, vibration will not affect the results, but if there is a loose fit, vibration is going to affect the results, it is going to impact again and again. The way we understood the erosion, where the individual particles were there, but here the whole metal will impact with a much larger velocity, larger impact energy. We can solve this kind of problem by providing suitable fits, choosing proper fits, so that where is getting solution from the fits from the system design. Similarly, we can think about vibration isolation. So, again we are saying that where phenomena, the cracking is getting its solution from some other streams. It is not a choice of the material, it is not a choice of the lubrication, but it is a complete system design. If I want to remove this kind of problem, I need to think from the other angle. We have one case study on cracking related to the roller bearing, which we will be discussing in the next lecture. Let us discuss about the final wear mechanism for this course. As I mentioned initially, there are more than 34-35 wear mechanisms. We cannot cover all the wear mechanism because this course is not exclusively for the wear. We have selected 6 wear mechanism, and in the list of the 6 wear mechanism, fretic wear is the last mechanism. It was coined, this term was coined in 1927 by Tomlinson. Tomlinson is a famous guy who have given the molecular theory of friction. He could show that there is a molecular attraction between surfaces, and he could propose some sort of empirical relation to find out what will be caused from friction, and he could show that softer material will have a more problem related to molecular attraction. And when we are talking about the fretic, we are talking about very low magnitude vibration, low magnitude and high frequency vibration. Energy is coming, but at the low magnitude or low amplitude, but proper word we can say that is the low amplitude in terms of 1 to 300 micron, it will not be detected easily. Some machine is running and we will not be able to see the vibration as such, but 1 to 300 micron vibration between two components happening, and that is causing the fretic wave. Is this a high frequency? low amplitude. So, overall energy comes from the higher side. In addition to that is oscillatory motion also. We are saying that this kind of mechanism, this kind of failure generally occurs in assemblies. Number of possibilities, it can be press fit, it can be coupling, can be riveted joint, can be bolted joint, where there is a possibility of micro slip. So, we have studied about the friction mechanism, static and kinetic coefficient of friction. We know very well when we are applying force, there will be some asperities, a irregular surface, and one surface has to climb on another surface. Quite possible we will apply some force, low magnitude, surface will move on a micro or nano scale and come back. That will not be easily diagnosed from the outside, but it is happening, and that is that micro motion, that low amplitude motion is causing the phoretic wear. Now, this is one of the common example. Of course, what I show an assembly is more like rusted assembly, but we are not talking about the failure because of the corrosion, we are talking about the failure about because of the fretting. Now, if you open this nut from the bolt, you will find some sort of powder, that will not be corrosive powder, but that will be particles coming from iron or related to that. Of course, the corrosion is increasing the wear rate, but it is not initiating. Initiation happens because of the fretting, and after that there is a more and more surface areas available, some chemical activity of those particles is the higher side, that is causing failure, right. Just to demonstrate same thing what we are saying, there are, let us take a one surface, another surface, they have a contact, they have a contact under the load, that means contact is under the stress. In addition, they are getting some sort of oscillatory motion, some sort of periodic motion, which is continuous, and we are talking about this motion of the in terms of micron, which will not be detectable, right. That is going to cause a problem. In other words, I can think about hinge mechanism. You can say there is a plank and there is a hinge. This hinge is not going to will be stationary. So, point which is a plank point or plank line which is in related to the hinge will remain stationary, but this line will move up and down continuously, it will be vibrating. So, what will happen? This is there is a relative motion, it will impact upper surface, it will impact the lower surface, and that impact is going to generate a micron scale particles. Continuous impacting micron to nanoscale particle will be removed from the surface, and as this particle removal increases, this oscillation also will increase. If the material is not there to restrain this Planck amplitude, then amplitude will continuously increase. So, from a micro slip to the slip and then to gross slip, phenomena will happen like that. And that is why I am saying that fatigue happens something like that. Initially there is a strict phenomena, we are pushing it to a certain value and relieving the load is we are not doing intentionally, but load is coming from outside from other factors that will cause some slip, micro slip, and initially the slip is a low magnitude, slowly the material is getting removed from the surface, the slip will turn out to be gross slip, and that thus gross slip is harmful. If something like that, we bought a new component, new assembly when never used, it was lying in on the table or we say some assembly which was vibrating with a very small magnitude, and that magnitude vibration created a problem and the whole system collapsed because of the fatigue corrosion or fatigue wear. This is the what which mentioned, if many times a nut and bolt connection kept as it is, when you open it, after that you will not be able to tighten, reason being that most of the powder from the nut and the bolt will be removed, thread profile will get damaged, and you again retighten this that nut bolt connection, it will not be, because there will be loose connection or threads, otherwise we need to recondition those threads if you want to reuse the assembly. So, this is what I mentioned about that, it introduces micro slip to the gross slip, and that cause a failure. These are the couple of pictures from outside surfaces look very nice, very shiny, no problem as such. When you open it and look at the micro scale, this is a 20 micron scale thing, you can see the pit. Pit is generated, outer surface is not damaged much. Of course, it is showing an irregular surface, but pit is generated at the center of this, where outer surface remain without much motion, but at the center most of the material has been removed. And depend on the material, they have a different color. It's something like if I am using aluminum material, I will find some sort of black color aluminum oxide powder. When I open the assembly, the failure will be there. Similarly, when we are talking about the iron material is the iron material, then it can be either iron oxide or ferrous oxide, or it can be the black powder which we generally observe, that is iron oxide again, and here the red ferric oxide, which many times we get in assemblies, right. So, either black color aluminum or black color iron oxide is one option, and red color, which is most frequently we get because of the rusting nature, and there is a slight difference between rust and corrosion. We use a word corrosion, corrosive wear initially, but here the word is coming as rust. This is only the small change. We say that corroding media, if it is a water, then it is a rust. If corroding media is something else, then it is a corrosion. So, if the water is acting as a corrosive media, then whatever the phenomena happens, that is a rusting, otherwise it is a corrosion, right. And if we understand this kind of a phoretic corrosion, phoretic wear, in this case I am using a word again phoretic corrosion, because phoretic is a starting point, and when it generates a number of particles, and if there is a air available or medium is available in manner, all those particles will get oxidized. When they get oxidized, their hardness also increase, and that is why they increase the wear rate. So, many times we use the word phoretic wear, and many times we use the word phoretic corrosion, because the starting is a phoretic mechanism leading to the corrosion and overall increase in the wear rate. There is mechanical action continuously. So, phoretic come corrosion and mechanical action is the phoretic corrosion wear. Now, we say that if we know the material table and we know which materials are susceptible toward the phoretic phenomena, then we should never use those material if we know the vibration phenomena is going to happen there. Like a titanium, titanium is one of the very costly material. If it is not used properly, it will cause a failure. You must have heard about this phoretic failure of the bone joints. So, you know that there is a bone cement which will be restricting the motion of implant, but if there is some micro crack in that, or there is a motion that will give some micro slip initially and then gross slip, that will cause a damage of the implant. So, that is also related to the phoretic wear, which can be studied in detail if we go on the micron scale or nano scale on that. Now, this is last slide on the phoretic wear. We can continue wear topic in our next lecture. I will prefer to use a word wear analysis, where we try to analyze the wear mechanism. Now, we have studied various mechanisms, but when we see the failure in totality, whether really one wear mechanism is going to be pointed out or it will give the results, or a combination of the wear mechanism are going to give us the results. So, that kind of wear analysis is important, whether we should choose material or we change the material, or we should provide a lubricant, or we change the system design, how to deal with the problem, that will come in a wear analysis. That is we are going to discuss in the next lecture. Thanks for your attention. Well, we will discuss on wear analysis in the next lecture. Thank you.